Okay, back again, and we're now starting with question 13 from test 2 from Math 107. It says, one version says the probability student is a BCCC student is a Maryland native is 45%. So that means the probability that a BCCC student is not a Maryland native would be 1 minus 0.45, which gives you 0.55. And it says, if 3 students are selected at random, find the probability that at least one of the 3 is a Maryland native. So probability of at least one Maryland native. So if you recall, let me grab another colored pen here, at least one, we have a formula for that. And at least one is 1 minus the probability of none are Maryland natives. At least one is 1 minus probability of none. So up in question 12, if the probability of a Maryland native up here was 45%, in question 12, we also found the probability that none of the 3 were Maryland natives. So we're going to use this version from question 12. So we're going to take 1 minus the probability that none of the 3 were Maryland natives, if the probability of each one was 45% to be a Maryland native. That answer was 0.166. So we're going to take 1 minus our answer from number 12, the first version, 1 minus 0.166. And that's going to give me my answer of 0.834. Why do we have that formula? Remember, at least one of something and none, they're complementary events. The only way to not have at least one of something is to have none of them. The other version of question 13, let me move this up so you all can see it, goes to the second version of number 12. And this says the probability the BCCC student is a Maryland native is 55%. So the probability that a BCC student is not a Maryland native, complementary event, would be 1 minus 0.55, which would be 0.45, 45%. And this question says, the version of the question is, if 3 students are selected at random, find the probability at least one of the 3 is a Maryland native. When the probability of a Maryland native is let me draw a line here, is 55% in this version. So at least one, again, that's the complementary event, can't talk here, to none. So we're going to take 1 minus the probability of none of 3 are Maryland natives. And so if we go back up, let me move this down for a second, to question 12, when the probability of a Maryland native was 55%, the probability that none of the 3 were Maryland natives was 0.091. So the probability of at least one Maryland native is 1 minus the probability that none were Maryland natives. So that's 1 minus that answer we found from question 12, the second version of question 12, 1 minus 0.091, which gives you 0.909. So again, the probability when the second part of question 12 that none of the 3 were Maryland natives was 0.091. We use that answer to find the probability that at least one is a Maryland native. That's 1 minus the probability that none of the 3 were Maryland natives, which we got if the probability of a Maryland native was 55%. So going to question 14. 14 says a computer password consists of 3 lowercase letters followed by 2 numbers. In that version of the question. So remember, 3 letters, there are 26 choices. Numbers from 0 to 9 gives you 10 choices. That's what you're starting with here. So first version of question 14 says, how many different passwords are possible when repeats are allowed? So 3 letters followed by 2 numbers, fundamental counting rule. So 26 letters, 26 letters, 26 letters, 10 numbers, 10 numbers, because repeats are allowed. So 26 times 26 times 26 times 10 times 10 gives me 1,757,600 possible passwords. The other version of question 14 says 2 letters followed by 3 numbers. From 0 to 9. So again, 2 letters, 26 possibilities, numbers 10 possibilities from 0 to 9. How many passwords are possible when repeats are allowed? So 26 letters times 26 letters, 10 numbers, 10 numbers, 10 numbers. Fundamental counting rule. So 26 times 26 times 10 times 10 times 10 gives you 676,000 possible passwords when repeats are allowed. The other version, that's 14, going to 15. 15 says a computer password consists of 2 letters followed by 3 numbers, lowercase letters. Repeats are not allowed. So 2 letters followed by 3 numbers from 0 to 9. No repeats. So again, a 5-character password, fundamental counting rule. So 2 letters, 26, then 25 because of no repeats. Then 3 numbers, 10, then 9, then 8 because of no repeats. So 26 times 25 times 10 times 9 times 8 gives you 468,000 possible passwords if there are no repeats allowed. The other version of question 15 says 3 letters followed by 2 numbers from 0 to 9. No repeats allowed. Again, a 5-character password, fundamental counting rule. 26 letters, 25 letters, then 24 because of no repeats. Move that up, sorry. And then 10 numbers and then 9 because of no repeats. So if I multiply 26 times 25 times 24 times 10 times 9, I'm going to get 1,404,000 possible passwords. I feel like on this one I had a mistake in the answer key because I was doing it about 1 in the morning. And I did fix that. So if you took the version before I fixed the answer key, I hand graded it and said, no, you got credit for that, and put a note in there. So sorry about that. I got to start doing my work earlier in the night, right? Okay, so on to number 16. 2 versions of 16. One of them says 2 letters, lowercase, followed by 3 numbers. From 0 to 9. And one of them says, how many passwords are possible? So we're going to draw 5 blanks, again, using the fundamental counting rule. When the first letter must be A and the last number must be 7 and repeats are allowed. So this can only be A, only one possibility. Then this can be any letter, 26, repeats allowed. So it could also be A. Any number 10, but the last number can only be a 7, so that's only one possibility. So that's going to make 2,600 possible passwords for that version of number 16. The other version is you've got 3 letters followed by 2 numbers from 0 to 9. Again, 5 blanks, a 5-character password, fundamental counting rule. And it says how many passwords are possible. The first letter must be an A. The last number must be a 7 with repeats allowed. So the first number has to be an A, only one possibility. Then 26 letters, 26 letters. Repeats are allowed. So they could be A's. Then we have 2 numbers. This can be any of 10 numbers, but this must be a 7. So only one possibility there because it can only be a 7. So 26 times 26 times 10 is going to give you 6,760 possible passwords. Okay, so going to number 17. How are we doing for time? Plenty of time here. I'll leave this up here so you can see that. Okay, so going to 17. One version of 17 said, how many different ways can 6 people line up in a single line at a grocery store? So 3 different ways to do this problem. 6 people could be first, 5 could be second, 4 could be third, then 3, then 2, then 1. Multiply that out. That's really 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. Or you can do, because order matters in a line, you'd rather be first than last, you can do 6p6. They all give you the same answer, which is 720. The other version of 17, question 17, is how many different ways can 5 people line up in a single line at the grocery store? Which if only we could all go to the grocery store now together, right? So that's sad. But anyway, 5 people in line. So 5 could be first, 4 could be second, 3 could be third, then 2, then 1. One way to do that. That's 5 factorial. But because in the line order matters, we could call this 5p5 a permutation. Any way you do it, it's 120 different ways. Number 18. Says, in a committee of 12 members, how many different ways can the president, vice president, secretary, and treasurer be chosen? So order matters. You have 12 people. You're choosing for 4 offices. Order matters because they're different offices. So that's 12p4. If you have from 12 people, you're choosing 4 for different offices. And so if we calculate that, we're going to get 11,880. And again, in one version of this, I think I had the wrong answer at the beginning for the first couple of you who took it, but then I fixed it. But anyway, I hand graded all those questions just to make sure. The other version of that question, you have 14 members in a committee, and you want to choose the president, vice president, secretary, and treasurer. So that's 14p4 because order matters when they have different jobs. So if I do 14 permutation 4, I'm going to get 24,024 possible ways to choose 4 people from 14 when they have different jobs, so order matters. And number 19, in a committee of 12 members, how many different ways can a subcommittee of 4 members be chosen? So we don't care about the order chosen. They all get the same job. They're just on the subcommittee. So that's a combination. So 12C4, which is 495. The other version of that question is, in a committee of 14 members, how many different ways can 4 people to be chosen for a subcommittee? Order doesn't matter because they all get the same job. It's a combination. So 14C for combination 4 gives me 1,001 possible outcomes in a combination. My husband, my coworker, is coming by here. Okay, so I'm going to stop here because I'm at 13 minutes, and I'll do another video starting with number 20.